Yeah, let's look for some examples before we do this. The complete picture in Control System 2 also contains a third part in this picture dealing with the Z-plane. Note that the Z-plane is defined in Chapter 7 in my Control System 2 lecture. This has something to do with digital filters. So the digital transfer function of a filter written in coefficients of the Z term also has a stability criterion, but then wait for a Control System 2 lecture. Let's do, before we go to the next criterion, look for some examples. First example is very simple. Is a PT1 stable, or could a PT1 be unstable? Let's check this with my criterion. The transfer function of a PT1 is given in workbook page 16, k divided by 1 plus pt. Poles, there is only one pole. The pole is that p where the denominator is 0, so this is p infinity 1, only one pole, which is negative 1 over t. Yeah, if you put for p, replace p with negative 1 over t, you see the denominator becomes 0. This is a condition for a pole. If this is given, then apply my condition. This is real, and stability is if this is negative. So this is very simple, converted to the time constant t, stable if and only if, short, stable if t is positive or 0. If t is 0, we have also a stable system. Let's check this also with my simulation program. In the simulation program, we will do this. Of course, you can ask, can a t be negative? I can tell you, yes, of course, not in a passive RC system, of course, but in an active PT1, of course, time constants could also be negative, and systems can become unstable. We will do this in our example number 2, but here you see if time constant is a positive, system is stable. If time constant is negative, system is unstable. Let's just quickly start the simulation and check this with my simulation program. After start, just take a PT1 block, positive t, this is just okay. One problem is, of course, this program can only calculate the step response, not the impulse response. But of course, the step response is also a very good indicator for stability. The final value then should not be 0, but constant. Or also amplitudes should go down to 0. If I do this, you see the step response ends up in a constant final value, and then this is a good indicator for stability. What happens if time constant becomes negative? This is possible in this simulator. If time constant is negative and we redo this calculation, then you see there is an exponential function with increasing amplitude. Here you see after 1 second we are at the amplitude negative 20,000. So also the step response can be used as a good indicator for stability. Theoretically, we use the impulse response, of course, but also with the simulation program, we can very easily check stability. So far. Next example. If you call this example for 1, then this is the example for 2. We make now a very simple addition. We take our KT block and add a positive feedback. positive feedback and want to have the new transfer function, FFP, which is using the equations to simplify signal block diagrams with positive feedback. In the numerator we have k over 1 plus pt, and the denominator 1 now with a minus sign, and the transfer function of the open loop system. This can be simplified in k multiplied numerator and denominator with 1 plus pt. So we have 1 plus pt minus k. Pole calculation gives the following example. K, the numerator doesn't matter for stability, denominator is a polynomial function, so we set now 1 minus k plus pt, we set to 0, then we have a definition for my pole. If we solve this, we have p infinity is 1 over t. On the right side we have then the k minus 1 part. Okay, this is the pole of my closed loop system, and of course the sign, this is a real number, so we have just investigated the sign of this expression. Of course the sign depends on the sign of t and k. K can be positive or negative, any value between negative infinity to positive infinity. T could also be positive or negative, so we have to investigate two cases. Case t positive, then we see if k is positive, stable if and only if, stable if p infinity is negative. So we have to check is stable if 1 over t k minus 1 must be negative. If this is positive, we have only to investigate the sign of this. So stable if k is smaller than 1. Okay, that means unstable if k is larger or equal 1. The equal one we have to check, is this really a case with equal 1? 1. Let's investigate this case with my simulator. We open this simulation program, we add a positive feedback, so we need a sum here, branch, feedback branch without a negative sign, and we have first the case that the time should be positive, k is 1. So let's assume, go back to the example here, stability if k is smaller than 1. So just check if we have an 0.5, then this should be stable in spite of positive feedback. Not all positive feedbacks cause instability. If you check this, you make a recalculation, you see final value is now 1, stable, constant, so we assume this system is stable. Now we increase the k to 1. What happens if k is 1? We have indifferent state. This is the situation. This must be negative for stability. If this is 0 or positive, we have instability. In the case 0, this could cause an indifferent state. What happens in my simulation program? Let's see. we see a ramp function, constant increase. That is the step response of an integrator. Note that the impulse response is a constant value. We have now a step response. It's the integration of the impulse response is a ramp function. And this is also the indifferent state. And if the k is now larger than 1, so let's calculate with 2, then we can see the recalculation cause an explosion. Yeah, we go up to 40,000 after 1 second. So this is a good indication for instability. What happens in the next case? We have case 1. Now we discuss case 2. If the time constant of the open loop system is negative, we know this is an unstable open loop system. What happens? We have an unstable system with a positive feedback. So the first idea is instability with open loop and then an positive feedback, which causes normally instability, is double instability. But note, our situation is exactly defined with our pole condition. We need stability, so this pole must be negative. So 1 over t multiplied with k minus 1 must be negative for stability. Now this is negative, so at once we can say, okay, if this is negative, this must be positive. Yeah, this part must be positive. So stable if k minus 1 is larger than 0 or k is larger 1. Yeah, unbelievable, but true. I will explain you this very quickly, what happens in this case. If k is larger than 1, we get stability. For all other cases, instability. That has to be proven here with my simulation program. Now I click to negative time constants, case 2. I start with 0.5. What is with 0.5? My equation says 0.5 stable for larger one, so this must be unstable. Check. Step response, click, clock. That looks very unstable. So, yeah, very clear, positive feedback, unstable system. No, really a miracle. Next step is the border case is positive 1. So I check with positive 1 simulation. What happens with again 1? Say OK, and we get now a negative ramp, but this ramp is an indication. Step response ramp means indifferent case. That is the impulse response constant value, border case. And finally, we check if k is smaller than 1, so 0.5 is unstable, 1 is unstable. So if k is larger than 1, then we get stability. Yeah, let's do this. I set the k to value of 2, negative time constant, calculate this, and you see, oh, that is an indicator for stability. A constant step response final value is a stable system. So you see, if time constant is negative, with a positive feedback, you get a stable system. You can stabilize an unstable open loop system with a simple P controller with positive gain. In this case, yeah, that means very simple. Normal systems with negative time constant have also negative k. That is, the inverted pendulum, for example. If you analyze the inverted pendulum, then you get a transfer function with negative k and negative time constant, and then a positive feedback with a negative k, the same as a negative feedback with a negative k. With a positive k. So we have here a negative feedback, and that means an unstable open loop system can be stabilized with a negative feedback. So first examples are clear. We make more examples in the next step. Now let's do an example number 4.3. Example 4.3. I want to show you that this criterion has limitations. Let's assume we have the following closed loop system coming from chapter 3.9. Remember, we have discussed this situation. Negative feedback, P controller, all gains are 1. We have 3 PT1s, and if the time constants are not given, we want to check stability. The open loop transfer function can be easily written, because this is a product of the P controller on the left side with 3 times PT1s, 1 plus PT1, 1 plus PT2, 1 plus PT3, and the closed loop with negative feedback can also easily be written as K divided by 1 plus PT1, 1 plus PT2, 1 plus PT3 divided by 1 plus open loop function. So, if I multiply with the denominator, I get the following new transfer function, which is 1 plus PT1 multiplied with 1 plus PT2 multiplied with quantity 1 plus PT3 and finally plus K. This is a closed loop transfer function, and the poles of this denominator, the zeros of this denominator are the poles of the system, has to be calculated to check stability. N is 3. The manual work is very complicated. Manually complicated. I can confess that in my time of study 30 years ago, more than 30 years ago, then the teacher tells us the poles, the zeros of a polynomial function with n 3 or larger are impossible to calculate if the numbers are not given. Then today we know that there is a method for n3, but if n is 4 or higher, this is impossible. So at this time we only can calculate the zeros if the t's are given as times, numbers. So this pole criteria comes to limitation because of the order of the denominator polynomial function. If n is 4 or larger, it is impossible to calculate the zeros of these polynomial functions. Stop. And for this we need better criterion, and this comes then in the next video. Number, which number is this? This is 44. 44 with the Hurwitz criterion. Hurwitz criterion. So this here is video 43.